Hey, and welcome back to solving a truss by the method of joints. So if you're just picking up with us, where we started before was if you haven't seen part one of the video, feel free to go back and check it out. If you have, where we started was we were given a problem where we have a truss and we need to solve for all member forces due to the applied loads using the method of joints. So we talked about some of our assumptions, we looked at solving reactions, and now we're on to sort of step 3 here, right? Step 3, which is solving for the forces at each joint. So if you're just picking up with us, that's pretty cool. What we're going to do is we're going to go down to solving the forces for each joint. Okay, so to do that, what I like to do is, to just look at one joint at a time. So here we go. We're going to come back to our diagram for a second. And when I look at joints, what I like to do is I like to say, well, first off, let's pick an easy joint, right? It's always better to start with the easy stuff, right? And it makes your life easier as well. So that's pretty cool. Let's find some low-hanging fruit and just go after it, okay? So when I look at the method of joints, there's a couple things that I look for. I look for a joint with 2 members, because 2 members typically has 2 unknown forces, okay, which you can typically solve with your 2 equations, some of the forces in the x and some of the forces in the y. In addition, if there are any horizontal or vertical members, I try to look for those. So in this case, what do we have? Well, we have a horizontal member in AB. So I would say let's pick joint A or joint B to start with, because both of those have horizontal, or both of those will have a horizontal member framing into it. Okay, we can pick either one. We could do BY, we can do, or B, we can do A, and for the purposes of this, let's just go to A. It's fun to start with A, so let's go to joint A. Okay, so we'll go to joint A and we'll start there. So typically what I do is I start by just going here and just drawing a free body diagram of joint A. So all of the free body diagram of the joint is a point. You don't even need a straight edge for that. That's kind of nice. But with that point, what we want to do is we want to put down all the known and unknown forces that we have. So on joint A, what we know is we're going to have AY that acts down, and that's 4 kips. Okay. In addition, we know that we have AX that acts to the right. That's 4 kips. I'm sorry, not 4 kips. That one's at 12 kips. Got to go back and look at right above here where we say, well, AX equals 12 kips. Good. So we're looking at our free body diagram. We transfer that down. And when we cut a part of this free body diagram out, what we're really doing is we're kind of chopping members off, right? So what we're doing is we're sort of like, cutting a circle around this thing. And when we do that, we're chopping and exposing, some member forces in these members. Okay, so let me draw that a little bit nicer here. So what we're doing is we're exposing these forces. Okay, these forces, we don't know what they are, but when we cut the joint apart, we have to account for those forces in our free body diagram. So this will be like the force that's in member AB, right? This will be the force that's in member AC. So what we have to do is come back down to our joint and draw those forces in. So I don't know what those forces are, but I know they exist, right? So I know they're here. I'm going to call this AB. And I know, this one here is here, and this is force AC. The other thing that I know is, because this is a truss, because again, if we come back up to our assumptions here, we said that these are all 2 force members. Okay, these are 2 force members, meaning the force has to line up along the axis of the member. Okay, so because of that, we know that the components are going to be at the same angle as the member. So what we're going to need to do here is use the member geometry at some point to relate the x component to the y component. Okay, so where we start here is I'm just going to draw those components in. I'm going to say, well, if AB is horizontal, there is no component. Because AB is horizontal, we know it's already in the x direction. For AC though, we know that there's going to be, let me try that again. For AC, we know that there's going to be a vertical component, and there's also going to be a horizontal component. So let me label those. I'll label this, ACY, label this one ACX, and I like to dash those in so that I don't get confused and I don't, double count them with AC, right? These, we can use the components or we can use the main vector, but we got to use one or the other. Okay, so after that, it just comes down to our 2 basic equations of equilibrium. So at a joint, all the forces pass through that joint, so there's no moment created at that joint because the moment arm is 0, right? There's no distance for those forces that are away from the joint. So what we're going to do is we're just going to use some of the force in the x direction, some of the forces in the y direction, and start to solve. So as we get here, let's try that again. What we're going to have is some of the forces in the x direction equals 0. So let's start with that, right? And I'll just write down my forces. AX, we have ACX, we have AB. All these have to equal 0 when we add them up. What I like to say is any forces to the right are positive, so AB and ACX are both going to be positive. And what that also means is any forces to the left, like AX over here, are going to be negative. So we know AX, we can write this in, minus 12 kips, plus ACX, plus AB, equals 0. And the problem right now is we've ended up with an equation that has two unknowns, right? We don't know ACX and we don't know AB. So this is where sometimes you guys get stuck and just give up. But the good news is we have another formula. Let's use that formula and see where it goes. Sum of the force in the y direction equals 0. So if we do sum of the force in the y direction equals 0, let's see what forces are in the y direction. Well, we have ACY, we have AY, and that's it. So this has to equal 0, but again, ACY, we're going to say anything that's going up is positive, so ACY is positive, going down is negative, AY is negative. So what we're going to get is ACY equals AY. And we know AY from when we solve for reactions, so we can say, well, ACY equals 4 kips. Okay, so check, that's good. We got box 1, and we're good. What that allows us to do here is take ACY, and it doesn't allow us to directly plug it in for ACX, but if you remember, AC is a two-member force. So what that means is if you have member force AC, we're going to have components here that look like ACX and ACY, right? So these will, if we add tip to tail, ACX plus ACY, we're going to get AC. We're going to get to the same point in terms of the magnitude of that force. So the other thing that we can look at here is we can say, well, what's the geometry of that member? Right? We know the geometry of that member. If you come back up to the problem, you'll see that this is a 3, 4, and we're going to have a 5 triangle. So let's just take a look at that for a second. If we have the geometry of this thing that looks like this, I think we have 3, 4, and 5. That's a 3 foot, 4 foot, 5 foot triangle, right? What we can find is we can find this angle, right? And we can use cosine, sine, and tangent to relate, 3 to 4 to 5. Similarly, that angle is the same angle up here. That's still theta. So what we can do is we can use that relationship between the angle to relate ACX to ACY, ACY to AC, and we can solve for each of those. So what we can end up doing is writing some equations that look sort of like this, right? So we can say, well, okay, I'm just going to use similar triangles here. So let me put it this way. If I take the tangent of theta, y'all should know what the tangent of theta is. And the tangent of theta is just the opposite over the adjacent, right? So if that's true, what we know is that's going to equal what? ACY over ACX, which is also going to equal the same angle, same theta, 3 over 4. You see that? So what we're going to do here is we're going to use this relationship to figure out ACX and ACY. So if we're going to figure out ACX. So if I multiply both sides by ACX, multiply both sides by 4/3, I'm going to get ACX equals 4/3 of ACY. Okay, so now I can plug in ACY, get 4/3 of 4 kips, and ACX equals, well, it's 4/3 of 4 kips. I get, when I do that out, I believe 5 1/3. 5 1/3 kips, okay? So that's ACX. Once I know that, right, I've used my angles and my geometry of the members and understanding these are two force members to solve for ACX. I've got ACX, I've got ACY. I'm going to plug ACX back in up here, and I should be able to solve this now. So now what I'm going to do is I'm going to try and solve for AB. So I'll move everything else to the other side. I'll say AB equals 12 kips, And remember, if we move the ACX to the other side, we have to subtract it now, minus 5 1/3 kips. So AB x has to equal 6 2/3 of a kip. Okay, so that's pretty cool. And actually, I don't need the x here because there's only an x component. I forgot. We're just doing AB. Okay, but what that gives us is it gives us AB, and it gives us ACY. One of the things you'll notice here is all of the values that we got were positive. What does that mean? Well, it means when we look at these forces, they're all pulling away from the joint. These forces are all positive. What we're saying, they're all pulling away from the joint. We got all positive values when we solve for them. That means that those forces are shown in the right direction on the free body diagram, which also means that because it's pulling away from the joint, what we're going to say here is, well, if we know it's pulling away from the joint, we're always saying pulling away from the joint is going to be tension. So in this case, we know AB is in tension. Also, we know ACX and ACY are in tension. Okay, so I'm just going to put T's here, right? We haven't actually solved for member force AC. So we've solved for ACX and ACY. Real simply, we could just say, well, AC has to equal the square root of ACX squared plus ACY squared, right? That's using the Pythagorean theorem. Okay, or we could, again, come back to our geometry over here. We could say, well, we know that what? The sine of theta equals ACY over AC, which also equals 3 over 5. Okay, so we can use this relationship here. Okay, oops. And so we can use this relationship here to solve for AC. So either one works. You can do either one. You can plug either one in. This, comes down to an equation that says AC equals 5/3 ACY, right? If you multiply both sides by AC and by 5/3, which is going to mean we have AC equal to 6 2/3 of a kip. Okay. And what we'll also want to do is we'll want to make sure we box our answer so it's real clear, and also say that that's also in tension. Okay, be careful if you use Pythagorean theorem, because if you have two negatives, right, the square of two values is always going to be positive, so you just have to be careful with that. That's one of the reasons I like using this geometrical method and the trigonometry a little bit better. So that's joint A. That's the first part. And hopefully that makes sense. If not, feel free to stop it, go back, look at it again, right? Then we have to pick again. So once we do one joint, we have to come back up here and we have to pick and say, okay, we picked one joint, where else do we want to go? So we have to pick another joint to solve. Again, we looked for easy joints to solve. We like to make our life easier. Okay, so what I'm going to do is I'm going to take a look at, joint B now. So if I take a look at joint B and I cut that, well, we know we have BY. We know we also have some force in here that's going to be BC. We know we have some force in here that's going to be AB. Right, so when we cut those members, we have to account for them. So let's go down, let's draw our free body diagram, solve, and the neat thing is, when we're all done, we've solved for all three members. We never had to do joint C. You can do joint C just to check your work, but we never needed to, right? So we could use AB and BC here and solve for all three forces that we're looking for. So let's go down. We'll draw a free body diagram of joint B and keep solving. So here we go. We could say joint B. And what does this look like? Again, free body diagrams and joints are pretty easy. Just draw a dot, okay? So we have a joint. We know we have BY acting up, and that was 4 kips. We know we have AB, and AB is going to be in tension, so it has to pull away from this thing. And if AB is in tension, it's pulling away, and we're saying that AB was equal to, I believe we had 6 2/3, right? 6 2/3 of a kip. And the other force that we're going to have here, actually I'm going to move this down. I'm just going to say AB equals 6 2/3 of a kip. The other force that we had was our force, what was it? It was if this was, you know, joint B, this was force BC. And again, forces at an angle is in a truss. They're two force members. They have to align with the member. What we're going to do is we're going to draw our components in. So we're going to say we have components here. We're going to call this BCY. We're going to call this, you know, BCX. And we can go ahead and use our equations of equilibrium to solve. So let's start there. Let's go. Okay, so let's do sum of the forces in the x direction equals 0. Again, that method of joints, you're using sum of the force in the x. Sum of the forces in the y direction equals 0. I'm just going to write these out because I know I'm going to use them. Okay, so sum of the forces in the x direction, we get AB, you know, and BCX has to equal 0. We look at the signs. Anything to the right is going to be positive. Nothing's going to the right. They're both negative. A lot of negativity here, but hopefully it turns around and we get some positivity back out of it. Let's go. So what we're going to get is if we had BCX to both sides and flip it around, we're going to get BCX equals minus AB. So what we say is BCX equals minus 6 2/3, right? So this was just, the 6 2/3 was just substituted from what we got before. So if you remember, you know, we solved for AB up here was 6 2/3, and now we're going to say, okay, when we plug that in, we're going to get BCX is 6 2/3. Okay, so that's pretty cool, except we get a negative value. We don't like negatives, do we? Well, it's okay. What a negative means is this negative basically means the arrow that we drew on our free body diagram is in the wrong direction. So in our free body diagram, we assumed that the force BCX was pulling away from joint B, right? And that means when we assume that, this shows tension. And when we get a negative sign, all that means is that we're now in compression. Right, so instead of the arrow pulling away, it really should be, right, this arrow really should be pushing towards joint B. I'm not going to flip it around right now. I'm not going to change things. You know, but if we move on to later problems, we could, you know, we could put it in the correct direction. Okay, but for this one, all I'm going to say is it is pulling away. It is negative, so that means we're in compression. Right, so let's go to sum of the forces in the y direction. Again, sum of the forces in the y direction, all we have are BCY and BY. I didn't label it down here, but this is BY of the 4 kips. Okay, and so what do we have? BCY and BY AST equals 0 when we add those two together. Right, there's no component in the y direction from AB. So those are both on the free body diagram, both going up. We're going to call them both positive. So again, we're going to get BCY equals minus BY, and BCY equals minus 4 kips. Pretty cool, huh? Okay, so where we go there is we have BCY is minus 4 kips, compression. Okay, again, if you get one component in compression, both components need to be in compression, and both components and the overall resultant needs to be in compression. Okay, so what I'm going to say here is I'm going to say, well, BC, okay, I'm going to use the Pythagorean theorem here and kind of show you one of the things you need to be careful with. So I'm going to say BC equals the square root of BCX squared plus BCY squared. Again, all we have here is a force triangle. So we have some force, I'm sorry, drawn it in the wrong direction. We have some force, you know, BC, and we have components, right? So we have components BCY, BCX, right? So if we have, you know, BC and BCX and BCY, this is a right triangle. We can just use Pythagorean's theorem to solve for the you know, BC. We don't even have to get into the geometry of it. That's pretty cool with this last joint. So let's do that. So when we do this, we say BC equals the square root of, what do we have? We have minus 6 2/3 of a kip squared plus minus 4 kips squared. Okay, and when we solve this, we kind of need to know also that there's going to be a negative value out here because all of these are negative. So what I'm going to say is I'm going to say BC equals, when you do the math out, I'm going to say minus 10.15 kips. Okay, so you know this number, it's you kind of have to know that this is in compression. And the reason you know it's in compression is because the two components are in compression, right? This arrow has to go in the same direction as its two components. You can't have it in the flip direction. So That's it. I mean, if you wanted to keep solving this, you could continue to joint C just to double check your work, but this is where we're at. So I hope that this method really helps you, or this video helps you. But as we went through it, what did we do? Well, we started with looking at the problem, assessing it, drawing a free body diagram, solving for the reactions, and right now what we did is we went through and we solved for the forces at each joint. Okay, so hope that helps you, and if you have questions, feel free to drop me a line. But until next time, keep working hard and keep going ever onward and upward. We'll talk to you soon.